You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your IT Fundamentals certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. In this episode, we focus on how processor speeds are measured and why they matter. You'll learn what the terms megahertz and gigahertz mean, how they relate to clock cycles, and what role they play in evaluating system performance. Processor speed is a concept that appears frequently in device specifications, advertisements, and exam questions. Understanding it helps you compare CPUs, make sense of performance claims, and recognize how speed fits into the larger picture of computing hardware. Processor speed is referenced in Domain 1 of the ITF Plus exam under Common Units of Measure. It also connects to infrastructure and performance topics in later domains. You may be asked to compare devices based on their listed CPU speeds or explain how megahertz and gigahertz relate to one another. While the exam will not test deep-level CPU design, it will expect you to interpret these units correctly and apply them to everyday computing scenarios. Processor speed refers to how many operations a central processing unit, or CPU, can perform per second. It's often referred to as clock speed because it's governed by a timing signal that synchronizes the flow of instructions. The faster the clock, the more instructions a CPU can process in a given period, though other factors also play a role. Speed is typically listed in megahertz or gigahertz, and knowing the difference between them is essential. The base unit of clock speed is the hertz, abbreviated as Hz. 1 hertz equals 1 cycle per second. This unit is used not only for processor speed, but also in other areas of computing and electronics, such as memory timing and network frequency. It provides a universal way of describing how often something happens, and in the case of CPUs, it describes how often the chip can perform a basic task or step in its instruction cycle. 1 megahertz, or MHz, equals 1 million cycles per second. This unit was common in older processors, microcontrollers, and embedded systems. For example, early home computers operated in the range of 4 to 33 megahertz. While MHz is largely replaced by gigahertz in modern systems, it still appears in legacy documentation and in specialized environments, such as industrial controllers or low-power embedded chips. 1 gigahertz, or GHz, equals 1 billion cycles per second. This is the standard unit for modern consumer CPUs. Most laptops and desktops today operate in the range of 1.5 to 5 gigahertz. When someone says a CPU runs at 3.2 GHz, they mean it can perform 3.2 billion cycles every second under optimal conditions. Gigahertz has become the dominant label for evaluating clock speed in modern systems. To compare megahertz and gigahertz, remember that 1 gigahertz equals 1,000 megahertz. This conversion helps when interpreting specs across generations or understanding why one value may appear faster than another. Gigahertz is used for mainstream consumer devices, while megahertz might still be used in support documents, chip specifications, or niche components. Understanding both units ensures you don't misread performance information. A clock cycle is a signal that tells the processor to perform one unit of work. Each cycle may fetch an instruction, perform a calculation, or move data within the CPU. Modern CPUs use pipelines and multiple cores to execute many instructions at once, but the clock cycle still governs the pace. The higher the frequency, the more times the chip can perform these actions per second, allowing faster execution of programs and smoother system responsiveness. Processor speed affects overall system performance in noticeable ways. A higher clock speed means more instructions can be executed in a shorter time, which improves multitasking, file processing, and system startup. However, speed is not the only metric. A slower CPU with better architecture or more cores may outperform a faster one in real-world tasks. That's why clock speed should be considered alongside other factors when evaluating performance. While it's tempting to equate higher gigahertz with better performance, that's not always accurate. Modern CPUs rely on many other design factors, including instruction sets, thermal management, and the efficiency of each cycle. A chip with a lower clock speed but better cache, more advanced architecture, or wider pipelines may complete tasks faster than a higher clocked processor. The ITF Plus exam emphasizes understanding the general role of clock speed without assuming it is the only performance factor. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. In this episode, we'll break down how processor speeds are measured using frequency units like megahertz and gigahertz. These measurements, often printed on boxes and spec sheets, represent how fast a computer's central processing unit or CPU operates. Understanding what these numbers mean helps you interpret performance, compare devices, and answer exam questions with greater confidence. We'll also cover how speed relates to system responsiveness and when it should or shouldn't influence purchasing decisions. Processor speed appears in Domain 1 of the ITF Plus exam under Common Units of Measure. It also connects directly to infrastructure concepts covered later, especially when examining computer components and performance factors. You may encounter questions that ask you to distinguish between megahertz and gigahertz, or choose the better performing CPU for a scenario. By the end of this episode, you'll understand not just what the numbers mean, but what they don't tell you. Processor speed, also called clock speed, is a measurement of how many cycles a CPU completes per second. Each cycle allows the processor to perform an operation, such as moving data, executing a calculation, or processing part of an instruction. A faster clock speed means more cycles occur each second, allowing more instructions to be completed. Speed doesn't operate in isolation, but it is a foundational element of overall system performance. The unit used to describe these cycles is the hertz, abbreviated Hz. 1 hertz equals 1 cycle per second. For example, a 1 megahertz processor completes 1 million cycles every second. A 1 gigahertz processor performs 1 billion cycles per second. The higher the number, the more operations can happen per second. While hertz is used in other areas like sound and radio frequencies, in computing it directly refers to the pace of CPU activity. Megahertz, or MHz, was once the standard unit for describing processor speed. Early home computers and business machines ran in the range of 4 to 33 megahertz. Even though modern systems now use gigahertz, you may still see MHz listed in documentation for embedded systems, microcontrollers, or technical specifications for small electronics. Megahertz is also relevant when comparing historical systems or reviewing legacy support requirements. Gigahertz, or GHz, is the standard unit for modern desktop and laptop processors. 1 gigahertz equals 1000 megahertz. Most current consumer processors run between 1.5 and 5 gigahertz. A CPU rated at 3.2 gigahertz performs 3.2 billion cycles every second under ideal conditions. This range supports most general computing tasks, from document editing and web browsing to media playback and moderate gaming. To compare megahertz and gigahertz directly, just remember the simple ratio: 1 gigahertz equals 1000 megahertz. This is the same relationship as between kilobytes and megabytes, or between kilobits and megabits. Recognizing the conversion helps you interpret older specifications or compare low-power devices like routers or embedded boards with newer, faster systems. It also helps clarify system documentation where both units may appear. Each clock cycle signals the processor to perform a basic unit of work. These cycles govern how quickly the CPU fetches instructions, decodes them, and executes them. Modern CPUs use advanced techniques like pipelining and branch prediction to increase efficiency, but the cycle remains the fundamental timing mechanism. Without clock cycles, a CPU cannot synchronize its actions, and speed would be impossible to quantify. Understanding this internal rhythm provides deeper insight into processor behavior. Clock speed affects performance in many tasks. Faster CPUs can complete instructions more quickly, which improves multitasking, application responsiveness, and file processing. High speed is especially noticeable when performing demanding operations like video encoding, file compression, or complex simulations. However, not all tasks benefit equally from increased speed. Simple functions like browsing the web or checking email may not see major improvements from a higher gigahertz rating alone. It's important to understand that speed is only one piece of the performance equation. Two CPUs with the same clock speed may perform differently depending on their architecture, core count, and cache size. A newer CPU may execute more instructions per clock cycle, making it more efficient. Other factors, like instruction set enhancements and memory management, also influence how effective each cycle is. That's why judging a CPU by clock speed alone can be misleading. There are also physical limitations tied to speed. As clock rates increase, so does the amount of heat generated. Processors require cooling systems to dissipate this heat, and at a certain point, thermal output becomes too high for consumer devices to manage. Power usage also increases with speed, which affects battery life in mobile devices. Many laptops use CPUs that throttle performance to balance speed, temperature, and energy efficiency. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Different use cases require different priorities. A user who only needs to write emails and browse the internet won't benefit much from a high-speed CPU. In contrast, a professional editing high-definition video or running virtual machines will need both a high clock speed and multiple processing cores. The ideal processor balances speed, efficiency, and suitability for the tasks it will perform. That's why smart buying decisions go beyond gigahertz alone. The ITF Plus exam may ask about processor speed in multiple ways. One question might show two devices and ask which is faster based on gigahertz. Another could ask you to identify the correct unit for a clock speed choosing between MHz or GHz. You might also see a scenario-based question that links CPU speed to workload performance. Familiarity with these formats ensures you're prepared to apply knowledge in the exam's context. To summarize, processor speed is measured in hertz, with megahertz and gigahertz describing how many cycles a CPU performs each second. While faster speeds generally improve performance, many other factors, such as architecture, cache, and core, shape how well a processor handles real workloads. By learning how to interpret speed correctly, you gain the tools to compare devices, support user needs, and succeed on the ITF Plus exam. Modern CPUs include multiple cores, and each core can process its own thread of instructions independently. Clock speed still applies to each core individually. For example, a quad-core processor running at 3 GHz can execute up to 12 billion cycles per second in total across all cores, assuming balanced workloads. More cores allow better multitasking and higher parallel performance, especially in programs designed to use them efficiently. The ITF Plus exam may not dive deep into multi-core design, but knowing that speed and core count work together is essential. Another key component that affects how speed translates to performance is the CPU cache. Cache is a small amount of ultra-fast memory built directly into the processor. It stores frequently accessed instructions and data so the CPU doesn't have to fetch them from slower main memory. A processor with a large or well-managed cache can complete more tasks per clock cycle. Architecture also plays a role. Some CPUs are more efficient per cycle due to improved pipelines, instruction sets, and scheduling. Thermal and power considerations limit how fast processors can go. Higher clock speeds produce more heat, which must be managed by cooling systems. In laptops and mobile devices, power efficiency becomes more important than raw speed. These devices often use CPUs that run at lower gigahertz to preserve battery life and reduce heat. Some systems include dynamic scaling, adjusting CPU speed based on demand. Understanding this helps explain why mobile processors don't always match desktop performance even at similar clock rates. Different types of devices prioritize different performance factors. Smartphones often run between 1.8 and 3 gigahertz, using efficiency cores for background tasks and performance cores for demanding apps. Desktops, with more power and better cooling, maintain higher sustained clock speeds. Servers and workstations focus on consistent throughput under load and may include many cores running at moderate gigahertz. Each use case involves trade-offs between speed, thermal output, and reliability. Marketing can make CPU speed seem more important than it is. Manufacturers often advertise the highest possible clock rate, known as turbo speed, rather than the base speed. This can be misleading, as most CPUs don't run at maximum speed all the time. Actual performance depends on workload, thermal conditions, and system configuration. That's why professional reviewers rely on benchmark testing to provide a more realistic picture of how processors behave under different workloads. Clock speed affects performance in different ways depending on the task. Video editing and rendering benefit from both high speed and multiple cores, since these tasks involve complex processing and large data files. Web browsing and document editing are less demanding and can run well on CPUs with modest gigahertz, provided they have fast cache and efficient core design. Gaming is a special case that relies on a balance between CPU speed, GPU performance, and memory bandwidth. Exam questions may present clock speeds in different formats and ask you to make comparisons or recommendations. You might be given a scenario that includes two CPUs, one at 2.4 GHz and another at 3.1, and be asked which is faster. You could also see a question that connects a user need, such as video streaming or spreadsheet use, to an appropriate clock speed. These questions are less about math and more about practical understanding. When estimating performance, start with clock speed but always consider other specs. If two CPUs have similar gigahertz, compare their core counts, cache size, and power ratings. Use gigahertz as a baseline, not a final answer. For entry-level system selection, this approach works well. Identify a speed range, then check whether the rest of the specifications align with the user's needs. This habit builds your ability to interpret specs in real-world tech support roles. It's also important to clear up common misconceptions about processor speed. First, a higher gigahertz rating doesn't guarantee better performance. It only tells you the number of cycles, not how much work is done per cycle. Second, gigahertz doesn't measure data transfer rate. That's a function of memory and bus speed. Third, gigahertz has nothing to do with storage speed. Your hard drive or SSD performance is measured in megabytes per second or input-output operations per second, not clock cycles. To reinforce these concepts, explore online benchmarks and comparisons. Sites that chart CPU models, gigahertz ratings, and performance scores provide a clearer view of how speed relates to real tasks. Practice reading product pages, noting how clock speed is presented versus how the product actually performs. This helps train you to look beyond flashy numbers and dig into what matters most when advising users or selecting hardware. Another good learning tool is comparing your own devices. Check the gigahertz of your phone, laptop, or desktop. Then use built-in task managers to observe how CPU usage changes with different activities. Watching how clock speed behaves during light and heavy tasks shows how dynamic processors are in practice. This real-world observation reinforces the technical concepts and helps you develop your IT instincts. To summarize, megahertz and gigahertz measure how fast a processor executes instructions by counting the number of cycles per second. While a higher number usually means better speed, true performance also depends on architecture, core count, cache, and efficiency. The ITF Plus exam may ask you to interpret these values or compare systems based on user needs. By understanding what gigahertz really means and what it doesn't, you gain the ability to support users, choose equipment, and think critically about performance. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.